Here's an example of a problem that combines at least three separate problems that are easy or relatively easy on their own, but here the challenge is to actually integrate across several chapters and topics of physics. We have a 3 kilogram block that is initially at rest on a horizontal surface. At time t equals 0 seconds, a force with magnitude of 12 newtons that is parallel to the surface begins to act on the block and accelerates it. The coefficient of kinetic friction between the block and the surface is 0.2. The question is, at what rate is the force doing work on the block at time 2 seconds? So let's look at the block here. Here's the horizontal surface and the block on top. Let me mark the force to the right that acts on that block. That will be the 12 Newton force, and I'll mark here the force as P. The block, of course, will move to the right, so this will be the displacement. I'll mark it here as delta L, and I will use the formula for the work of a force that is constant in magnitude and its relative direction to the displacement stays constant as well. So that's the simplified expression for work. Here, force times the displacement times cosine of the angle between the two. In this case, my force F will be the one that I marked as P on my diagram, to 12 newtons. Delta L will be the displacement of the block, and here both vectors pointing in the same direction means I will have cosine of 0 or 1, so the work here will be P times the displacement. I know P is 12, but the question is, what is the displacement here? We're not quite clear. Before we go to that, however, let's look at the question. The question is, what is the rate at which the force P does work? In other words, the question is asking for the power of that force at the time equal to 2 seconds. Let's start with the formula for the average power. The average power is always equal to the work done by that force divided by the time it took. So let's mark that time as delta T. On the other hand, I saw that the work of the force P has to be equal to the force P itself times the displacement delta L. So I can see that the power will be P delta L over delta T. If I want to know how much is that power, not as average over an hour or some prolonged period, but over a very tiny interval around the 2 seconds, I have to work with very small intervals, delta t. I will here take a limit when delta t goes to 0, and I can see that the ratio between the displacement over the time for that very small time interval is really the definition of instantaneous velocity from kinematics. So I can see that the power here at time 2 seconds will be equal to the force P, here 12 newtons, multiplied by the velocity at 2 seconds. So the question now is, what is the velocity of the block at 2 seconds? If only I knew what the acceleration of that block is, and if that acceleration happened to be constant, I could possibly use the kinematic relations for the constant acceleration motion, in which, particularly when I have what I have is velocity at any given time will be equal to the velocity in the beginning plus the acceleration times the time. Remember, this applies only if we have a constant acceleration. So the next question is, what is the acceleration of that block? And now 99% of the questions about acceleration are always solved through Newton's second law. And the first step in the dynamics analysis of problems is to actually look at the forces that act on a particular object. To that end, let me draw the gravitational force pointing downwards. I'll mark it here as mg. Here m is the mass of the block that is given 3 kilograms, and g is the gravitational acceleration, 9.8 meters per second squared. I will also have a normal force to account for the interaction between the block and the horizontal surface. I'll mark that force as n. Clearly the surface is not smooth, so there's kinetic friction. The problem actually even tells me what the kinetic coefficient of friction is. It's 0.2. So I will write that I will have frictional force pointing to the left with the magnitude equal to mu times the normal force. Remember, mu here is 0.2 and is what I marked as the normal force. With that, I'm ready to apply Newton's second law, which tells us that the sum of all forces as vectors has to be equal to m times the vector for the acceleration. The easiest way to add vectors, remember, is by components. In this case, naturally, all the forces are aligned either along the horizontal direction, which I will mark as x, or along the vertical direction, which I will mark here as y. So let's write Newton's second law for the components. For the x components, I will have to add all the x components of the vectors. So I will have a positive component of the force P plus 20 newtons. To that, I will have to add the negative x component of the frictional force, which will be minus mu n, and that has to be equal to m times the x component of the acceleration, which is a in this case. For the y components, I will have a positive n component for the normal force. To that, I have to add the negative y component of the gravitational force, minus mg, and that has to be equal to 0 because I do not have a y component of the acceleration. The vector for the acceleration points along the horizontal direction. So the second equation, the y equation, gives me directly that the normal force has to be equal to the magnitude of the gravitational force mg. If I put the numbers there for the mass and the gravitational acceleration, I find out that the normal force is 29.4 newtons. So from here on, you can actually see how the problem is going to unravel and we can find the answer. Knowing the normal force, I can go back here and plug it in the x equation where I had the frictional force, which will allow me to find the acceleration, and hopefully if that acceleration comes out constant, I can go back to the kinematic relationship about the velocity, use the acceleration there to determine the velocity, and then go back to the question about the power at 2 seconds. Since I don't have space here, let's open up some space. I'll move some things around here. Let's see what we had. The question here was what's the rate at which the force does work at 2 seconds. Because of that, we looked at the average power, and it turned out that the power for the 2 seconds, not just the average power, but the power at 2 seconds here turned out to be equal to the force P times the velocity v. Please note that P here is not power but stands for that pushing force P. We were trying to figure out what the velocity at 2 seconds is, and so because of that we needed the acceleration a, and that is what we're trying to do right now, find the acceleration a. For that we have to use the normal force value that we found that is 29.4 newtons and put it in the x equation that came from the application of Newton's second law, which gives me plus 12 newtons minus 0.2, the coefficient of friction, times the normal force, which was 29.4 newtons, has to be equal to the mass, 3 kilograms, times the acceleration. From here, simple algebra will show us that the acceleration has to be equal to 2.04 meters per second squared. Not only I have determined the value for the acceleration, but I actually see that it is constant. So indeed, I can use the kinematic relationship for the velocity. So velocity at any given time t will be equal to the velocity at time 0 plus a times t. The block started from rest, so at times equals 0 seconds, that velocity was 0. So what is left here is just to replace the symbols with the numeric values. For the acceleration, I'll have 2.04 meters per second squared. For the time will be 2 seconds, and I see that the velocity at 2 seconds is actually 4.08 meters per second. And now I can finally go back to the question of what is the rate at which the force is doing work on the block at 2 seconds. That will be equal to the pushing force P, 12 newtons times the velocity at 2 seconds, which is 4.08 meters per second. And for the final answer, I determined that the rate or the power at t equal 2 seconds is equal to 48.96 watts.